All right, as Blake mentioned, my name is Alex. I work on the operating systems team at CoreOS. And I wanted to take a few minutes here today and talk to you about Ignition. Before I get started, I'm curious, how many of you have heard of Ignition or use Ignition today? A couple people, good. Hopefully by the end of this, we can increase that number a little bit. So, Ignition is another one of our open source projects. Of course, we have CoreOS Linux. We have Rocket, our container runtime. We have Claire, our container image security scanning tool. etcd, the distributed database. Flannel, our network overlay technology. And adding to that group, we have Ignition. Now, I noticed that we have excellent icons for all of these, but nothing for Ignition. So I took a stab a little earlier at drawing one. I'm curious what you guys think. Huh? Yeah, looked a little better on paper. All right, so what is Ignition? So Ignition is a new utility that we've been working on for CoreOS, designed for provisioning the system. It works in a very early boot mode, which allows it a little bit more control over what it can do to the system. And we'll dig into that a little bit more. But the basic idea is you build a configuration for your machine, and you hand it to Ignition when the machine starts up. And Ignition does what it needs to get the machine into that particular configuration. Now, for those of you who are familiar, you might be asking the question, how is this different from CloudinIt? This sounds like exactly the same sort of problem that CloudinIt solves. And I don't want to dig into this too much because it was the topic of my talk at last year's CoreOS Fest, if you were there. But I do want to point out some of the two main differences here. And the one is that Ignition only runs on the first boot. The reason we do that is we want Ignition to be used for provisioning. Too many people are tempted with CloudinIt to try to shoehorn configuration management into it. So they'll use it to write some files, and then they'll change some files in the config, reboot the machine. And for the most part, it does a pretty good job of updating. But there are too many quirks and too many problems that introduces. And there's too many excellent tools already out there. Ansible, Chef, Puppet. That class of products already solves this problem perfectly. CloudinIt is not the right solution for that. So by running this only on the first boot, we ensure that you only use it for provisioning. You set up the disks, you set up the files, and then that's it. Ignition's done, it's out of the picture. From there, you use traditional configuration management tools to handle the lifetime of the machine. The other key difference is that Ignition's configuration is static. So if you're familiar with CloudinIt's format, you'll remember that it has these variables, these special variables that can be expanded, things like public address, private address. Ignition has no notion of this, and the reason is because if it only runs once, having dynamic data actually isn't that useful. It's only ever interpreted that first time. So it would end up being more confusing to users, and it doesn't quite fit the model of Ignition. And as we actually dive into the example, hopefully we'll see that a little bit. So what is this Ignition? What can it do? Obviously, it can take care of all of the same sort of tasks that CloudinIt does, but it does a whole lot more. So everything related to storage, Ignition should be able to handle. So partitioning your disks, formatting your partitions, setting up RAID arrays, all the traditional management tasks with your disks, Ignition can take care of. Additionally, it understands how to write systemd units and how to enable them, and of course configuring your network as well. There's some nice sugar built into Ignition that allows you to manage users and groups in the same way. So you can create users, you can create groups, you can assign SSH keys and passwords to these users, you can assign passwords to groups, all that sort of stuff. One of the really neat tricks that Ignition can do, though, is a configuration that you provide to a machine can actually reference a remote configuration. And it will go out and fetch that remote configuration and put the two together and evaluate that. And at first glance, that doesn't seem useful, but there are actually lots of cases where this can be used to an advantage. There's a particular cloud provider that many of you probably use that limits user data to 16 kilobytes in size. You can use these remote configs to actually bypass that limitation. So you'll feed the instance a stub config that then points to a much larger config stored elsewhere, maybe on S3, maybe, I don't know, it doesn't matter. Anywhere that's accessible over the internet. Ignition will take that stub config, go out and fetch the larger config, put them together, and then evaluate it. So why should you use Ignition? First off, it's subtle, but once you leverage the power of this, there's no going back. Systemd internally has a fairly complex dependency tree that it builds of all of the units on the system. So it knows what depends on what it needs to start in order to run something else. Because Ignition writes all of the units to disk before systemd starts, it means that systemd has a global picture of what the system should look like. And it means that you can fully utilize all of systemd's tooling to inspect that tree. So I can say, I have my example service. What other services depend on this before it starts? Or what services depend on my example service before they can start? All of these tools are actually very well built. You have systemd CTL, which can list dependencies. You can also use systemd analyze, which can actually draw out a full dot graph of the entire dependency tree. It's impressive. Additionally, Ignition does atomic provisioning. So if you have 20 tasks that need to be completed in the provisioning process, if any one of those fail, Ignition fails and will fail the entire boot and will drop you into an emergency shell. Upon first hearing this might sound like an inconvenience, but when you're running hundreds, thousands of these machines, it's nice to know that if you can SSH into that box, if that box joins the cluster, if it comes up properly, you know that it's in the state that you asked it to be in. You know that it set up the disks the way you wanted, it has the files in place, it's created all the users you expect, and once that machine is up, it's ready to rock. It has everything in place. If any one of those fail, you don't want it to join your cluster in this half-broken state. That's going to cause a lot of trouble down the road. It's going to be a lot of debugging. Ignition also does a better job of preserving semantics across environments. So because Ignition is built on very simple constructs, you don't need to know a lot of the internals of Ignition to use it across platforms. So whether you're on AWS or Azure or on bare metal, these same concepts apply to all of the machines. You don't need to know that, oh, on Azure I have these particular variables available to me. On EC2 I don't need to manipulate the disk in this manner. All of that operational overhead is out of the picture with Ignition. Ignition also uses static configs, which I mentioned before. These static configs don't have variables in them. It's a JSON structure. They're relatively simple. And there is no dynamic injection into these. Now I do have to pause here and address JSON. Every time I bring this up, I get a few complaints. Why are you doing this in JSON? Why not YAML? Why not TOML? Why not any number of languages? And the reason is because it is easy to read, but difficult to write, okay? The ideal language for us would have been one where it is perfectly readable by humans and impossible to write, okay? Now, obviously, this language doesn't exist and arguably cannot exist, but we think JSON is the closest thing to that. We've all tried writing JSON ourselves and included that trailing comma and screwed the whole thing. So we know the common pitfalls. We know that it's foolish to attempt to write JSON by hand, and we avoid it like the plague. And this is good. And the reason is because we found over the years, turns out humans are actually pretty bad at writing configs. We've all been there. We've all had our cloud config going, and we do a couple edits to it. We feed it to the machine. 2 minutes later, it comes up, and etc didn't start. We dig into it, and shoot, I forgot a space. The indentation is wrong. So you make that one little change. You feed it back to the machine. 2 minutes later, it comes back, and something else has failed. By the end of this, 15 minutes later, your keyboard's broken, and you decide you're finally just going to use the online validator. By using JSON up front, we encourage people to use some sort of compilation tool, right? So let's say we have this hypothetical tool that allows us to write a config in YAML, and then it translates it to JSON for us. By forcing the user to use that tool up front, we can do all of the validation right then and there before they even attempt to boot a machine. And iterating on that tool takes a matter of seconds rather than waiting for the full boot process. So in the end, it actually saves the users a lot of time, even though up front, it's not immediately obvious. Additionally, JSON is a very simple config language. Just about every language out there has full library support for generating JSON objects. And so it is very easy to write these hypothetical tools or to incorporate this output into your build pipelines. So how does this work? I think the easiest way to show this is actually showing a CoreOS boot process. So I have this nice diagram that I drew the other day. And this highlights kind of the rough overview of the boot process and the interesting milestones along the way. In this particular example, we're going to boot a machine and run etc, and we're going to assume we have a DHCP address, so something that we don't know at the time of boot, but we'll discover later. So we hit the power button on the machine. The first thing that happens is we bootload the operating system. In CoreOS's case, we use grub, the bootloader. And grub serves several purposes in our boot process. Number one being it loads our kernel into memory. The other task that it handles is detecting whether this is a first boot. Remember, we said Ignition only runs on that first boot. Grub is the utility that's actually responsible for determining if this is, in fact, a first boot. And the way it does it is by looking at the disk UUID. When we build CoreOS images, we have a magic known value. And if grub sees that, it passes an extra flag to the kernel that says, this is the first boot. And then what the kernel does later is it says, OK, randomize that ID so that the next time we come around, that magic ID is no longer present. Grub doesn't tell the kernel that it's the first boot. OK, so grub figures out if it's the first boot, loads the kernel. We leave the bootload stage and end up in the early user space stage. So this is the init ramfs, the init rd. This is the point in the Linux boot process that's traditionally used to mount your disks. So it loads modules, it loads whatever it needs to mount your disks. Now we piggyback on this process a little bit, and we fire off a couple extra processes. So assuming this is the first boot, we start up networkd, which configures our interfaces. Once that's up, we actually start Ignition. And Ignition will potentially use the network to go out to fetch additional configs, to fetch assets, to fetch whatever it needs to. Once it has all that, it'll write everything to disk. And then once it's successfully completed, and only once it's successfully completed, it hands it over to the pivot. The pivot is the last stage in the user space, early user space. And it hands control directly over to user space. Now, this is the point that most of us are familiar with. This is our running system. This is the point where systemd starts, PID1, on CoreOS. One of the first things that it starts in this process might be journald, which is the journaling daemon. Now, you'll notice that at this point, even though journald has just started, Ignition has long finished. So what this means is that Ignition is capable of writing all of your journal configuration to disk. So the moment journald starts, it has everything ready to go. So maybe we up the logging level. Similarly, networkd starts up, And again, we already have all of our network units on disk, so network D comes up, and maybe it assigns static addresses, maybe it changes the way that DHCP works. In this particular example, we're using the CoreOS metadata service, which is a small helper utility in CoreOS that can be used to find environment variables that describe the particular environment. So I'll give you an example because that's very vague. On EC2, if you run this utility, it figures out what the public address, what the private address, and what the host name are, and it writes that to a file. Once it's in that file, etcd can actually use those addresses and then bind on those particular ports. So etcd now can advertise its public IP address to the rest of the cluster. Once etcd is up and started, now we have the multi-user target. So this is the default boot target on CoreOS. At this point, once we reach this, we have a running system. All of our services have started. It's ready to accept work. We have a fully running system at this point. All right, let's see a demo. All right, for this demo, what I'm going to do is take CoreOS, which is roughly represented by this blue box here. We have the user A and B partitions, which are our active, passive update partitions. And then we have our root partition, which by default is ext4. Additionally, I'm going to attach 2 extra drives to this VM. We're going to call them VDB and VDC. So the first thing we're going to do to this machine is we're going to take this root partition and we're going to reformat it to Btrfs. Then we're going to take these 2 additional drives and we're going to drop a RAID array across these. So a RAID array, for those who aren't familiar, we're just going to take the disks and we're going to stripe the array across them so that we effectively build one big disk out of the combination of the 2 smaller disks beneath it. So once we have that RAID array device, we're going to format it with an ext4 partition, striped, and call it data. Once we have that, we're going to drop a single file on top of that. So this is what we're shooting for. This is what we're going to describe in our config. And I'll show you that config here. So that's our config. Everybody can read that, right? Good? OK, let's walk through it. So the first part of any Ignition config, of course, is the version number. Ignition configs are versions so that we can make changes in the future and remain backward compatible. So in this example, we're using version 2. The next thing we're going to do is configure those disks that we just talked about. So we have VDB, that first external disk. We're going to wipe the partition table on it, and then we're going to create a single partition called RAID 1.1. Similarly, we're going to take the second disk, VDC, again, wipe the table, and create a single partition on that one called RAID 1.2. So at this point, we have both disks partitioned. Now we build the RAID array on top of that. So we reference both of these devices that we just created, RAID 1.1 and RAID 1.2. We say create a stripe level RAID array, and then we're going to call it data. And we'll use data in the next couple of sections to reference this RAID array that we've just created. So the next thing we do, now that we have this RAID array, is we format the file system on the RAID array. So we specify the device, MD data, which was the name we just used. We tell it it's going to be ext4. And we're going to force create it. And the force create just means if there's existing data, don't worry about it, blow it all away, create a new file system. The last thing we're going to do is we're going to give it a name. Now, this name is a construct of Ignition itself. It does not propagate beyond Ignition. It's strictly for internal record keeping. So we can name this whatever we want, and it will only live inside of Ignition. So in this case, we're just going to call it our file system. And we use that ID when we create files. So in this case, we're going to create our config file. We reference the file system by the ID that we just used. We give it a full path to the file, in this case just config.json, and we give it a mode. Now, the mode here is specified in decimal. We're accustomed to seeing the file mode specified in octal, so 292 is 444 in octal, so read for both owner, group, and everyone else on the system. And the last piece of this is the contents. With Ignition, we can actually specify file contents by remote resources. So in this example, I have an example web server that I'm running, and what we're going to do is populate this file with the configuration that we actually pass to the machine, just to illustrate this. I don't think it's particularly useful in practice, but it's an interesting illustration. So at the beginning, I said we would walk through the config we hand to the machine. I lied a little bit. This is the config we're actually going to hand to the machine. And I'm going to show you the trick that I'm pulling here in a second. So let's walk through this. Again, we specify this is version 2 of the Ignition config. And then we say we're going to modify this config, and we're going to replace the contents of this config with the contents you find at this source. Now, what we find at this source is the larger config we just walked through. We're also going to throw a verification hash on this. So I can throw a SHA-512 hash. Obviously, that's not the full hash. And so when Ignition fetches this resource, it will hash it and make sure that it lines up. If it doesn't, it will fail the process. This allows you to ensure that you can throw that config wherever you want, and you don't really have to trust the transport. You don't have to trust the storage. As long as that hash lines up, it is the config you expected it to be. OK. Demo time. OK. So just to show you, this is the kernel command line I'm going to be passing to my machine. So we can see here that this URL, if we take a look at what's at that, we see this is the simple config we just walked through, obviously with the full hash this time. So let's launch this thing. So, oops, missed it. So we just flew through grub already. We're in the initRD. It's fetching the configs. You can see it's creating partitions at this point. This is going really fast. I'm really sorry. This boots amazingly fast. Never thought I'd have to apologize for that one. But so we can see at the end of this, oh, sweet. So let's see what's happening. So we created the file system. Something failed. The demo gods are not happy with me right now. Yeah, so actually, this is kind of cool. So this is what it looks like when Ignition fails. So we can see a start job is running for Ignition disks. We could go through this, but I don't want to keep you guys from getting drinks later. So what I'm going to do is kill this. We're going to go back to our backup copy, which is where we started from. And we're going to do this again. So second try. So we can see, again, more of the same. It's fetching the config. It's creating the partitions. It's finishing the partitions. There we go. And now we have a fully booted system. Second try. So now let's make sure that it did what we promised and I didn't just pull the wool over your eyes. So if we do a find mount on the root, we'll see that it's, in fact, btrfs, which is what I promised. We can also look at varlib data. This is the RAID array that we created. So the MD device is our RAID device. We can see that it's, oops, we can see that it's striped. And if we cat out varlib data config, we'll see the small config that we handed this. And the neat part is, remember we said we're going to actually take this and apply this. If we curl this directory, we should see that massive config that we walked through in the beginning, right? And sure enough, this is the massive config. So we have our disks, we have the RAID array, the file systems, all of that. Now, just to illustrate the last point, remember, Ignition only runs on that first boot. So how long did that take to boot? Did anyone time it? It's all right. I got it right here. It took 13 seconds to boot. Pretty slow. Let's reboot it and see if it's faster. Theoretically, it will be faster because Ignition doesn't run this time. It doesn't spend any time partitioning disks or setting up file systems, and it, in fact, does look like it was faster. This time it took less than 3 seconds to boot, so we shaved 10 seconds. So you can perform all of your long-running disk operations in this ignition phase, and you don't have to pay the price of that on every boot, just that first boot. OK, almost worked. Whoops, there we go. So what's next in Ignition's timeline? We want to spend a little more work improving config verification and encryption. So right now, it is only possible to fetch configs and resources over HTTP. This is because the initRD doesn't have CA certs. We want to make sure that we get that process right before we push it out to everyone. So in the future, we want to be able to use HTTPS to fetch the configs. We want to potentially use GPG to encrypt and verify configs that you fetch. Additionally, as I mentioned, this hypothetical tool before that could convert between these YAML configs and our JSON ignition configs, we need tooling that can do that. So that's where we're hurting right now. We have a lot of experimental stuff, but we don't have anything that we're really comfortable giving to the public yet. So if you have ideas, if you use Ignition today and you have ideas about what you need or what you would like to see, come talk to me afterward, because I'd love to hear it. And you're in a very unique position to heavily influence the direction we take this tooling. Better troubleshooting, obviously, when it comes to these early system boots, having as much logging and troubleshooting mechanisms as possible is better. And then lastly, we need more supported platforms. And this is just, we're slowly rolling out support to all of our platforms. Right now, we officially support bare metal systems. And there is very experimental support for EC2, Azure, and GCE. As we continue expanding this, we'll get support for all of the other cloud platforms as well. If you'd like to learn any more info on this, just go to coreos.com/ignition. There's tons of docs and examples up there. It should have everything you need to get started. If it doesn't, file a bug and we'll fix it. That's all I had. One quick final plug. We are hiring in all departments, so email careers@CoreOS if you're interested, or come find any one of our recruiters running around here. That's all I had. Thank you, guys. I think I probably have a couple minutes for questions. Does anybody have any questions?
OK, it's me again. So have you looked at HashiCorp's Vault? They have like an in-transit encryption mechanism that might be interesting.
I have. Yeah.
Cool. That was my biggest concern with shipping all the configuration over HTTP. But I guess my next question is, on boot up, it looked like there were a few, I guess, TCP dial exceptions. So is Ignite running a Go runtime right after the system boots?
Yeah, so Ignition itself is written in Go. So those particular errors you recognized were Go runtime exceptions. And what's happening there is, in the early boot, Ignition doesn't actually wait for the network to start. It just starts trying to fetch resources. It will back off if it fails. So you saw it took several seconds for the network to actually come up. It will wait and retry until it can get those assets, or until something times out. So those errors are actually expected. They're not the prettiest thing to see, but it is showing you that Ignition will try no matter how long that process takes. Does that make sense? Did I answer your question?
No, that does. Yeah,
okay.
That's cool.
Any other? Looks like we got a taker.
So people familiar with CloudinIt probably are used to certain things running every boot. What are your suggestions for doing something like running something every boot?
So if you want processes to run on every boot, you can leverage these standard systemd constructs. So typically, you will enable a process. And when you enable a process, it sets up a dependency between that process and a target. And so if you want something to run on every boot, you will tell it to install under the default target and enable it. And then that ensures that systemd will start it every time. The advantage of doing this, though, of course, is that it's up to systemd's discretion as to when to run that. And systemd is very good at starting everything in parallel and as quickly as it possibly can. So if you can give it all the dependencies up front, you can start that system in 2.7 seconds. Whereas with CloudinIt, it takes upwards of, for this example, probably would have taken about 5 seconds instead. Any other questions? All right, I'll hand it back to Blake. Thank you.